In this video we're going to take a look at some of the challenges from the HacktivityCon 2021 CTF. It's a 48-hour competition running from September 16th to the 18th, and let me just jump straight into some of the challenges. So as usual, I'll try and structure this kind of by the order of categories and also by the difficulty as well. So we'll start off with some of these warm-up challenges and work our way onto the other categories. The next challenge is called Pimple. It's a warm-up challenge, and the description says, "This challenge is simple, it's just a pimple." So we download the file to a local directory, and first of all you can see that it's already showing the file type, but let's check this in the terminal. And we'll see that it's a GIMP XCF image data, so let's try and open it up in GIMP. And you'll see that we have some layers down here. We can basically go through these layers and change the visibility to try and see what's underneath them. And if we work our way through the images, eventually we'll find that one of the images has this flag in it. The next challenge is called Tsunami. It's a warm-up challenge, and the description says, "Whoa, it's a natural disaster, but something doesn't seem so natural about this big wave." And we have this file to download, Tsunami, so I've downloaded that already. Let's go and do some basic file checks. We could have a look at the file type, and we'll see that it's a riff file, little endian, wave audio. We could try and do something like binwalk-e Tsunami, which actually finds this MySQL ISAM compressed data file. We could do foremost to see if it can extract anything there, and have a look at the output. You can see it's just grabbed the wave file, so nothing interesting. We could have a look for the strings. Let's do strings greater than 10, Tsunami. Got quite a few strings in here. Let's try and do that again and grep out flag. Nope. We might want to listen to it as well, but what I did here was open up Sonic Visualizer, as there was kind of a hint here about the wave. Let's open this up, and if we try to open the file, it's not going to work. We need to move it to tsunami.wave, and now we'll be able to open it here, and we can have a look at the data. So in some audio-based stego challenges, sometimes you'll see data hidden in some of these waveforms or spectrograms. So you can go here to layer and add spectrogram. We'll do all channels mixed, and this is already looking a little bit interesting. What's all this going on down here? So let's try and zoom in and move over towards this, and you can see here we've got a flag, and then we've got our curly braces, and we've got our hex value. So we basically need to just go through, type out that flag and submit it. The next challenge is called Base 64. It's a warm-up challenge, and the description says, "It looks like someone has base boosted this. Can you make any sense of it?" So we've got this Base 64 file which I've downloaded. This was solved by one of my teammates, so I'm just running through the solution. And we can print out Base 64. You see there's a lot of white space here, and then we've got these characters, all underscores and backslashes, forward slashes, pipes, etc. We could try and open this up in Sublime to see if it looks any different. Could zoom in and out. It's not looking too recognizable. We could take this to CyberChef as well, so let's go and have a look. CyberChef. The challenge title indicates there's going to be some Base 64 encoding involved. So if we go here and select Base 64, obviously this doesn't look like any Base 64 value that we would typically see, but we have there are some different base decoding algorithms, and we can select here as well the alphabet. So for example, we have alphabets which only deal with spaces and dashes and underscores, which is kind of similar to what we have here, although we do have some other characters as well. So if we go back to our terminal here and take a look at our string, let's try and minimize our terminal a little bit. Okay, still not looking too good. Let's try this again. Cat Base 64. There we go. So if we zoom out just enough, we'll actually see that we have some characters here. So we can go through and type these out. I, G, Z, S, Y, W. And if we go and type that whole thing out, we'll get a Base 64 encoded string, which I have copied over here. So we can paste this in and convert from Base 64, and we'll get our flag. The next challenge is called 64/2. It's a warm-up challenge, and the description says, I wanted to cover all the bases, so I asked my friends what they thought, but they said this challenge was too basic. And we've got the 64/2 to download. The title gives it a bit of a hint as to what it is, but let's take a look at the file. So I've already got this downloaded, and if we print this out, 64/2, we get this string. The first thing I did here was take this to CyberChef, and if we could solve this based on the challenge name, based on the hint, but what I did here was just throw this in here and type magic, and let CyberChef do the hard work. So it basically went through and tried some different decoding methods. You can see here that it found that from base 32 it was able to get this flag, so we can click that, bring up the recipe. This is the recipe we have here, and the title was a hint, right? So base 64 divided by 2 would be base 32. The next challenge is called Too Easy. It's a warm-up challenge, and the description says, these warm-ups are just too easy. This one definitely starts that way at least. And we've got this file to download called Too Easy, so we can download it. We can take a look at the file type, and we'll see that it's just a data file. So let's try and print it out, see if we've got any recognizable text, which we don't, but we could have a look at the strings as well. Maybe try and grep out a flag. But yeah, nothing of interest. So let's try and open this with hex edit, or we could do a hex dump on it to see what's going on, and we'll immediately see this file signature here is tooeasy.tooeasy. So we have jfif here, which is typically what we'd see for a image. So let's go and search to find out what the bytes should be, because it's these magic bytes at the start of the file which will determine what the file type is. So we can go here and say, what's the jfif file signature? And we could go and we could have a look on Wikipedia. It's got a full list of different file signatures. We can go and check here as well. What I actually did here was just go and download a jfif sample image, and if we grab this, we can also then do hex edit sample, and basically we're going to want to grab all of this. So let's go up to the end of the jfif. We want to grab all of these bytes here, so we could take a copy of them. We can't just go and paste them in here because of how this how the formatting will go. So I'm just going to move this Sublime window over here for now, and let's go and copy this over. So we've got ffd8 ffe0 0010. You can see this is already lining up to what we have there actually, so that's awesome. Let's save that, and let me now try to display that as an image. Display too easy, and we've got our flag. The next challenge is called Target Practice. It's a warm-up challenge, and the description says, can you hit a moving target? And the flag has 24 hexadecimal characters in it. So I downloaded this GIF image. It was actually a teammate who solved this challenge, but let's take a look at the solution anyway. So we've got this target.gif. It's I think got 24 frames in it. So we could try and open this up. Let's do stegsolve, and we could try to open the image there. We can then go through and check the different bit planes. We can also go and have a look at the frame browser, so we can go and have a look at each frame individually to see if there's simply a flag hidden here. I was initially thinking maybe it was like the count of dots on each frame which would make up the hex characters, but we've only got 22 frames here and it's a 24 hexadecimal flag. So we could save each of these here, but to save a bit of time, let's go and do this using an online tool. So we can look for GIF split and just go and upload the image, and then we can download a zip file with all of these frames in them. So let's download that. Let's unzip it, and then what we can do here is have a look for a barcode decoder. You can see this, we've got an online one which will deal with various different barcodes. So we're going to upload each of these images basically. We'll start off with the 21, and submit, and you can see the parsed result here. It doesn't look like a flag. We basically go back and try the 20th one, submit that. Again, doesn't look like a flag. And we can just keep going through this process. You could probably write a script, but I mean, in the amount of time it's going to take you to do that compared to just clicking browse a few times, it's probably not worth it in my opinion. But I think it was frame 15. Let's have a look. Submit, and you can see here then we get our flag. The next challenge is called Butter Overflow. It's a warm-up challenge, and the description says, can you overflow this right? So we've got some files to download, source.c and Butter Overflow, and we've got a server to connect to as well. I've already downloaded these files and launched the server, so let's go and take a look at it. We've got the source code, so we could just jump straight into that, but let's just have a look at the file anyway. We've got a 64-bit LSB Pi executable. It's not stripped. We can have a look at the protections on it, so checksec file butter, and we'll see that full railrow is enabled, so we won't be able to overwrite elements of the global offset table. There are no stack canaries, so we don't need to worry about tripping those off if we're overflowing the buffer. NX is enabled, so we won't be able to inject shellcode and expect it to execute on the stack. And Pi is enabled, so the base address of the binary is going to be different each time it loads. We probably don't need to worry about this because we can see it's a warm-up challenge. It's got very low points and a lot of solves. So let's just jump into the source code, which we probably don't really need to do either, but we'll have a look at it. So immediately we can see this give flag function, and we can see here it's going to open flag.txt. We don't really need to decode this too much. Let's jump down to the main part of the program. So we have our main function here, and you can actually see that it's reading in 200 hex bytes, so that's 512 in decimal. So if we were trying to work out how many bytes we need to overflow the buffer, as you can see here, this gives us a rough idea. So 512 is going to be kind of a starting point anyway. And we have this signal seg_v handler, which is basically going to say that if there's a segmentation fault, let's go back up here. If we have a segmentation fault, it's going to call give flag. So we have this handler set here, which is waiting basically just for us to crash the program. And so presumably we don't need to enter a specific amount of bytes, we just need to enter enough to overflow the buffer. So anything over, not 512, but maybe something close to that should give us the flag. And again, we don't really need to look at this too much, but it's just going to open flag.txt, it's going to load that, and it's going to print it out. So let's go and try this out. I'll make the program executable. We could just try this with like 512 bytes and then keep working our way up, but I'm going to do this as we would approach another, like a more complicated buffer overflow challenge. I'm going to open it in GDB pwn debug, and let's generate a cyclic pattern. We know that it's going to be over 512, so let's generate a cyclic pattern of 600 bytes, and we'll take a copy of that. We'll run the program, and it says how many bytes does it take to overflow the buffer. We're going to enter in here 600 bytes. It's going to crash the program because we overflowed the buffer there, and we basically want to look and see this RSP has this is where the return address would have been here. So if we take a copy of this and do cyclic-L to look up the offset of that, we'll see that it's at 520. So it looks like we need 520 bytes to overflow the buffer. But to verify that, let's open up, let's do Python 2-C, and we'll print A times, let's do A times 519 just to test this out. Let's run butter. Let's paste that in, and we don't crash the program. Let's try it again, and this time let's do 520 bytes, and you'll see here we get could not open flag file. So it looks like we've done exactly what we needed to do here, and we've got to this point where it's tried to open flag.txt and it's failed. So let's just say echo flag fake. Oh, can't spell, but who cares? We'll echo that to flag.txt. We'll run the program again, and we'll paste in our 520 bytes, and we get back our fail flag. So it looks like it's working okay. Let's just try this on the remote server. We've got this netcat we can connect to, and let me do the Python again. Python-C print Okay, we're doing Python 3 now apparently. A times 520. Take a copy of that and paste it in. Oh, let's try that again. There we go. And we get our flag back. The next challenge is called retcheck. It's a pwn challenge, and the description says stack canaries are overrated. And we've got this binary to download, we've got a server to connect to once we get things working locally. So I've downloaded this file, let's go and take a look at it. I've also got this open up in Geardra, but let's just go and do some basic file checks first so we can have a look at the file type. It's a 64-bit LSB executable. It doesn't have pi and it's not stripped, so we can go and have a look at function names and things like that, no problem. And each time the program loads, it's going to have a predictable address. We can check the binary protections as well. We can see that there are no stack canaries, although there was a stack canary mentioned here, so that's interesting. We've got full rel rows, so just basically means don't bother looking into overwriting global offset table entries. NX is enabled, so we can basically rule out injecting shellcode onto the stack to execute it, and we have no pi as we just mentioned there. So let's just actually make this executable and test it out first of all, just to see what it does. And we can see here retcheck enabled. We can enter in some characters maybe, see what happens. We could go back and do something like our last challenge where we could say the butter overflow, where we could say Python C print A times 512, print that out, try and run it again, and we get aborted this time, which is interesting. Let's go and take a look at this in Geardra and work out what's going on. So let's start here by taking a look at the functions, and we've got a main function right here which it's not going to do too much, it's just going to call the vuln function, so let's have a look at that as well. And in vuln we can see that we have this buffer declared of 400 characters. We also have this long in stack 000, but let's forget that for now and trace our way back from the buffer overflow, which is right here. So you can see that we're calling gets and we're reading the user input into this 400 character variable, but here we're not actually checking the length. We're just gonna say read everything until you find the new line. So there's no check, there's no bound check to make sure that what we're going to enter is going to fit into this variable. And the thing is, then we have this if in stack 000 is not equal to return address, we're going to get this abort. So we're going to go and check this out in GDB and see what this looks like, but let's just have a look here as well at the other functions. So we have a win function, which is basically just going to open a flag and print it out, and there's no points where this is actually called. If we go and have a look, show references to, there's no unconditional call to win, so we need to overwrite the return address of the function with the address of win to make sure it jumps to that. The problem that we're going to have here, and we'll demonstrate this in a second, is that we have this return address which is set at the beginning and it's set to this in stack value, and then at the end it's going to make sure that this still equals the same value. So if we overwrite this with something else, then we're going to get this abort function here at the end. So let's go and just demonstrate that in GDB. So kind of similar to our last challenge, the butter overflow challenge, we'll open this up and what's it called, retcheck. We'll generate a cyclic pattern. We could have a look at the functions here. So if, for example, you wanted to find the address of the win function to put this into your exploit, you can do that here. We could also just go and have a look at some of these functions. So if you wanted to find a specific address of a gadget or some data or something, you can do that in here as well. But yeah, let's do our cyclic, and we know that it's a 400 byte buffer. I'm going to do cyclic 500 then. I'm going to take a copy of this, I'm going to run the program, and let's paste this in and see what happens. And you can see here then that we've got this abort. You can see it's actually gone to kill, and we've got this stack check fail. So the problem was then that we didn't ensure that this return address still equaled the same value. So the best thing to do here, or what I did here, is we have this comparison which is basically going to compare what's in RDX and what's in RAX, and if they don't match, it's going to abort the program. So we could set a breakpoint right here, 401446. Let's do break need a star there. So we'll set that breakpoint, and we'll basically run through this again. Let's try and run the program. I'm going to grab my cyclic pattern again, the same pattern. Take a copy of that, paste that in there, and we're getting to the same issue. Did we hit our breakpoint there actually? Yeah, we've hit our breakpoint. We're at this comparison, RDX and RAX. So let's have a look what's in the RAX. The RAX is set to this address main plus 18. You can see that address right here. We could even go and disassemble. We could go and disassemble that and see what that's actually pointing to. So that's right here. And basically, if this address isn't in the RAX and the RDX, then we're going to get an error there. So what we want to try and find out is what is the offset to the RDX, because this is where we want to make sure we have this address in order to bypass that check. So let's do our cyclic-L and paste that in. And in this case we get 408. So that means we would need to write 408 bytes before we're going to overflow this RDX, and we want to overflow the RDX with the same value that's in the RAX to make sure this check passes. At this stage what I'm going to do is I'm going to jump over to a PwnTools script, and let's just see how we can code this. In fact, I'll copy this over. I'll just go through the process of setting up the exploit. So I have a template which I often use for these challenges. If you've watched some of my other videos, you're probably tired of seeing all this, but I'm aware that there'll be quite a lot of new viewers or viewers that maybe haven't seen the Pwn walkthroughs before. So let's copy this over to exploit.py. I'm going to open this up, and ordinarily there's a function in here to find the offset of the return address. I'm going to take that out, just simplify this a little bit, and we'll take this out here as well. Here's where we have this offset. What I'm going to do is say the offset is 408 to begin with. This is we know that we need to write 408 bytes before we get to our RDX, and then we're going to want to put in that address as well, which was let's go and grab that from GDB. So we want to make sure this address is in here, so I'm going to take a copy of that. I'm going to say that our canary is equal to, and we've got our memory address there, so we're going to write 408 bytes, then we're going to overwrite the RDX with the value that we need for that comparison to be true, and then we need to do our buffer overflow. Then we need to overwrite the return address. So let's say here we've got our offset. We'll say that what I'm actually going to do is I'm going to change this from a dictionary. Let's just make this a list, and we could just put in some A's or something here. I'm going to do offset, or I'll do ASM, do no operation instruction here. It's not really needed, but just a good practice to, rather than using characters, which could cause problems in some exploits, to use no operation instructions, which is normally hex 90. And we'll say that that is times offset, and then we're going to put in our canary value, which is that address we want to write, and then we want to return to win. So we want to return to that function called win, and we could paste in the address of that. So we could take the address from Deirdre or from GDB, as we saw there. What I'm actually going to do in this case is we're going to load in the binary. So I'm going to load in retcheck, and this will mean that it actually knows where the functions are. It knows what the addresses are because pi is disabled in this case. So we can actually just say here that we want to go to elf.symbols.win, and that's the return address we want to go to. I'm going to write the payload to a file just so that we can reuse it if we want to without having to run through this script again. And then the send payload after, you can see here that the last thing it sends to us is an exclamation mark. So I'm going to say after the exclamation mark, send a payload, and then we'll just jump straight into interactive to see what's happening. And that's about it. Just to mention here, we have so we can change this to debug to get a bit more information about what's going on whenever we run the exploit. And this is just to make it quite easy to swap between local, remote, and debugging with GDB, where we can set up a script here. So we'll see how we can do that remotely in a minute, but let's test this out. So I kind of want to see what happens in GDB as we do this. So what I'm going to do first of all is I'm going to run python exploit.py. You can see here we can actually see what's being sent and what's being received. We got end of file, so we didn't actually get our flag. let's have a look now. We've got this payload because we saved that to a file. So now what I can do is just go over here and we'll run this again, but we'll send in that payload. And you'll see that we hit our breakpoint because we've still got a breakpoint in at this comparison. And now we want to go and make sure that these match. And you can see here it does. We've got the same value in RDX and the same value in RAX. So that's our canary. And now we could step through this. So we could go next to make sure that was, the condition was true. And we could kind of just work our way through. So we can go here, go down to our leave. And what I noticed here is whenever we do that, we have our win right here, but we still need to deal with this this return address here, which is going to go to main 18. Because if I now go next, let's see, continue. So it didn't actually execute the win function. Let me go back to the code here, and let's just add in another 8 bytes before we get to our return address of the win function. So in here I'm just going to say asm nop times 8, and we can run this again here. You'll see that we get this could not open flag file, so we could actually go here and say echo flag to flag.txt if we wanted to test this out. We can have a look at our new payload here as well. And if we want to go and test this out then in GDB, what I'm actually going to do is I'm going to delete the breakpoints now. And let's run with payload. Okay. Where is the flag? Let me try that here. Let's run retcheck payload, and we get our flag here and the segmentation fault. Okay, I'm not too sure why that didn't actually. Let me put that breakpoint back. We have a breakpoint here. Let's run that again with payload. And we can again just kind of step through here, just hitting next to get through these instructions. You can see that now we have our no operation instructions here, where previously we had the return address. And it's gone to main plus 24. It's now gone to win. So if we go up here and have a look in the instruction pointer, it's set to win. So the next function it's going to jump to is going to be win, and we're in win now. But for some reason, oh, there's the flag right there. Okay. Yeah, it's just the output was kind of hiding it from me. Okay, well listen, that works alright. So what we can do, because we've done this Python script with the remote option, is we can just directly try this against the remote server. So let's take a copy of the server address and the port number here. And just to demonstrate, we can do Python exploit, that's local, and it's got us that flag. And now we can do the exact same thing, but just say in here remote, paste in that server and that port number, run it, and we get back our actual flag. The next challenge is called the library. It's a poem challenge, and the description says, welcome to the library, I'm thinking of a book, can you guess it? We've got the server launched here, but we'll try and get things working locally first of all. So I've already downloaded the library binary and also the libc library. First thing I might want to do is have a look at the file type again. Presumably it's going to be a 64-bit Linux executable, which it is. It's not stripped, so we're going to be able to see function names and things, and we can't see pi here, so it's going to have predictable memory addresses. But let's also use checksec as well, just to have a look at the protections. In this case we've got no stack canaries, so good chance it's going to be a buffer overflow. We still aren't going to be able to write over the global offset table, and we're not going to be injecting shellcode probably on the stack here to execute, and we know that pi is disabled already. So with that out of the way, let's just jump straight over to Deirdre, where I've already got the file open. And if we go over to our functions, we'll see that we don't have too much here. We don't have a win function like we did in one of our previous challenges. So most of the code, or all the code, is going to be in our main function here, which we'll have a look through now. So we can see that there's a buffer declared at the beginning. It's 520 characters. We can see that we're opening this file, dev_u_random is being opened, and then it's going to read 4 bytes from dev_random into this local 20 variable. It's going to call the rand to basically pick a random number, and then it's going to loop through. Let's actually run through this while we have that on screen as well. We'll run the library so we can actually see here what's going on. So you can see it's actually just printing out the different options in that loop, and it's then saying, I'm thinking of a book, which one is it? And it's asking us to enter a value. So if we enter in a value, we either get wrong, or if we happen to guess the correct value, we'll get correct. But whether we get this right or wrong, it's not actually giving us any opportunity to exploit or to leak anything. I mean, this dev_random, quite often you'll see on pwn challenges some random values being involved. So I guess it's kind of a bit there to throw you off a little bit, because in terms of the actual vulnerability here, it's the call to gets in our 520 byte buffer which is vulnerable. So it's not actually checking the length of the input that we provide. So instead of entering a 1 or a 2 or a 3 or a 4, we could actually just overflow the buffer. But we don't have anywhere to jump to, right? We don't have a win function here. We've got no function which is going to just read the flag for us. So we want to try and get a shell instead. You might want to go through some of this code, and you can hit L to rename these and say like buffer, or here we have our random value. And then if you kind of do that and step through, we can say this is rand file. If you have any particularly code that looks kind of hard to read, this might help a little bit depending on what you're used to seeing. But we know that we've got 512 bytes here, sorry, 520 bytes. Let's go and test this out in GDB and see if we can generate a cyclic pattern to overflow the buffer. So we'll run GDB pwn debug the library, and here we might want to generate a cyclic pattern again of 600 characters. We can take a copy of that, we can run through the program, and instead of entering one of these numbers, let's enter that cyclic pattern, and you'll see that we have our bytes are filling up the stack. And what we're interested in is what's the offset of the RSP here, because these are the bytes which would make it into the RIP if they were a valid memory address. So we can say here cyclic-L to look them up, and we'll find that our offset is at 552. So whenever we're going to put in our pwntool script here, we're going to put in 552 A's or no operation instructions or something, and then we're going to overwrite the return address with our exploit. We'll talk about that in a minute. We can also calculate this in pwntools directly, so I'll show how to do that as well. So let me copy over the pwntools template. You could actually get a better template here. I've got plenty of return to libc exploits which we could use, but I'm just going to copy this over and just kind of talk through as I'm doing it, just in case anybody who's watching is unfamiliar with how to write these scripts or how to do the exploit, and it might help a bit if I go through it in steps. So this template here, let me zoom in a little bit. We can change first of all, most of this stuff up here is just part of the template, so all we're going to do is go and change the name of the file here to the library, and that means it's going to find everything it needs to about it. It's going to find out where the functions are, it's going to find out that it's 64-bit and what operating system and stuff, so that we don't need to worry about any of that when we're building up our exploit. We're going to set this to debug as well, just so we get some more information. And if we were having some problems with our exploit, we could go in here and set up some breakpoints. Let's say we want to break at the main, or we want to break at a certain address. We can do that in here, and then just launch the script with the GDB argument to debug. Or we can launch it locally or remotely. And the last thing then is this find IP function, which you can see is going to identify the RIP offset. So instead of us finding that in GDB, we could set this to, let's say, cyclic 1000. I'm just going to comment this out for now. And if we just run that as it is, do Python exploit, and okay, we got -1 there. Let me go back and see. Let me try and run the program again. So run the program. So yeah, it's asking us, it's providing this angular bracket. So you might have to update this function depending on what it asks you for here. So it's just kind of a helper function. You can see that what I actually needed to do here was comment out the bit for the 86 for 32-bit application, because we're in a 64-bit application here. So let's try that again. And this time it'll tell us that the offset is at 552. So that's exactly what we found in GDB, and it's using the same cyclic function as well there, cyclic find and the cyclic pattern as well. So we do that in here, but we could just as easily say the offset is 552 if you prefer doing things manually. And then we're going to start the program. So let's start putting this payload together. So because there is no interesting function to exploit here, what we're going to do is we're going to use a two-stage payload. The first stage is going to leak some address, so we could leak put, so we could leak printf or gets or something like that. And once we've leaked that, we'll know where that function is in the libc library on the server or locally whenever we're testing it locally. Once we've got the address of one of these functions, we can calculate our way back to the base of the libc, and then we'll know the offset to any of these functions, which means we can just call any function that we want out of libc. So for example, system. And we can also similarly just find the strings in there as well. So we'll be able to find the bin sh string and pass that to system. We might need to grab some ROP gadgets as well to do that, but let's look at putting together the first part of that payload now. So we'll need to, I'm going to use the puts function here. So let's first of all find a pop RDI gadget. So I'm going to use ROPA to do this. You can actually do that from Pwn debug, but let me just do ROPA -- file the library, and we're going to search for pop RDI. So we've got this function here. I'm just going to copy this part, and we'll say that our pop RDI is equal to 0x and paste in that address. And if we're building up this payload, we're going to say that at this offset, so at 552 bytes, the first thing that we want to inject is going to be pop RDI, and that's going to pop the next thing in this payload into the RDI register. And what we want to do there is puts. Let me see, actually, does it show here for puts? If we highlight puts, you can see there that in the second parameter there, RDI, is where we want to put the string. So let me pop RDI, and we're going to say elf.got.puts, and that's the address that we want to leak. So it could be something else. We could say that we want to leak elf.got.get or something like that. I'm just using puts here, and the thing is that in order for us to leak this address, it has to be used. So the global offset table is going to get populated with the address of the functions which are called. So you can see the functions here. So it's going to look into libc on the system, and it's going to find out, because every version of libc is going to have different offsets here, it's going to find out where the offset of this particular function is, and then it's going to save it locally in the global offset table. So if we leak this address here, we need to make sure that puts has already been called, or that we're calling elf.plt.puts. And after that, we want to return back to our main function, back to the start of the program. Because we haven't actually got a shell yet, we need to keep going on to the next stage. So we'd need to keep looping through the program until we build up our payload. In this case, there's only going to be 2 stages to it. So here we can say elf.symbols.main, and I'm using the elf.symbols and elf.plt.puts, but you could just go and find these addresses yourself as well. You could go into GDB or Adair or something like that and look for info functions. Oh, let me info functions, and you could grab the main address here and just kind of copy that and paste this in here. So it's just a different way of doing things. Because we loaded the binary here, it knows where all of these things are. And that's it. It's going to leak our first address. What I'm also going to do here is set up, let me just copy this over I'm going to define the libc library here as well. So this is my local libc library. If I do, I need to stop opening so many terminals. If I do ldd the library, you can see that I can get my libc library here, and then we've already downloaded the same libc library that's used remotely, so we'll get things working locally, and then it'll just be a case of commenting this out and update and uncomment in the remote libc version, and then we should be able to test it remotely. Let's also take some stuff out here. So I'm not going to save the payload to a file because this is a multi-stage payload anyway. We're not just going to be able to send the file. I'm also going to take that out because we want to get a shell, and we're just going to send off the payload and it'll go to interactive. So we might want to just test this out first of all. Let me run that Python exploit, and you can see that it's run through there. It's leaked out this address, which looks like a libc address. We can see the 7F there anyway. It's looking good. So we need to format this into the correct format, and again I'm just going to copy over a chunk of code that I normally use on these. So we send off the payload, and then we're going to receive the leaked address. This is basically just going to unpack it into the right format, so we'll see the format that this puts it in. Let me run that again. In this case, we also need to receive a line, so sometimes you'll just need to do io.receive or receive line, or lines. You can basically go through, as long as you've got debug mode on, you can kind of go through and determine what's going on. Let's try that again. That didn't work. Did I save it? I don't think I saved it. Oh, I'm receiving the line before I'm sending the payload. Okay. Receive line. So we run that again. This time we've got this leaked got.puts, and we want to maybe make sure that this is the right address and that everything's gone right. If we want to do that, we could go to GDB. So if I run this again with GDB in capital letters, it's going to open up this GDB window, and we've got this breakpoint here set at main. So let's hit continue, and it's gone into interactive mode here. You can see we've got this leaked address. So what I'm going to do now is go to our GDB window and say x, and then paste in that address, and you can see that it's told us that this address is where the puts function is. So it's correctly leaked the puts function, and from here we could go and try and find out what the system address is. I think if I do p minus and system, no, okay, let's do p system. So there's the system address, so we could say, it's been a while since I did some of this stuff in GDB, as you can see, but we can find out the address there. We could get that in hex as well. So this would be the offset. So we could basically say that we could go and manually say, now if we want to call system, we could just leak this got.puts address, and then we could basically use this offset to go and call system straight away. But a better thing to do is to find out the offset to the base of the base of libc, and then you can just call other functions from there. But this is a good way to just go and verify that everything's going correctly. So if we're finding some of these offsets manually, we might go and say, let's do LDD again on the library to see what my libc version is, and we could do readelf-s, and this will basically show us all of these offsets. So we can just go and grep out system and find out what the offset is, and then we know that if we leak the system address, so let me do that again actually with puts. So here's the puts address. So we know that if we subtract this from the value that we've just leaked, we've got the base of the binary, and then if we add this to that base, we've got the address of system, and we can do things like that. We can also find the bin sh string that way, so we could do strings-t x and provide that same libc address, and then just grep out bin sh, and we'll find that the offset to bin sh is from here. What we can do also here, which I think is pretty cool, because we've defined the libc binary here and we've just found out what the address is, we can go ahead and update that so that it'll be mapped to all the functions. And this means that if we're doing things remotely, we can just swap the libc file that's being used, and it'll update everything automatically. So we've leaked out the got_puts address here. What we're going to say is libc.address is equal to got_puts minus the libc symbols.puts. And this is basically going to set the base address of this libc binary to the address that to the correct base address, and that means we can go ahead and call whatever we want to. So let's just say that is the leaked libc base, and we can start putting together our next payload. So the next stage of the payload, we're going to try to get a shell. So we're going to pop into the RDI again, but this time we want to pop the bin sh string. Now there's a couple of different ways we can do that, but because we've got our libc library, we can actually just say next libc.search, and then we can search for the string. So we'll search for bin sh. You can put a null byte there as well, although it typically seems to work without it. And next we'll be calling system, so we can just do elf dot sorry, not elf, we need libc dot symbols dot system. And we don't need this return address, so this should work for us. All we need to do is send off that payload again, send off this new payload, and then hopefully we'll have a shell. Let's try that out. Python exploit. Okay, we've leaked the libc base there, but we haven't got... okay, let me go back to the... So we were waiting to send it after we received this angular bracket, but you can see the angular bracket was already sent up here whenever we receive this line. So instead of sending this line after we receive that, we'll just say we want to send the line. And let's try and run that. This time it runs, it says we're wrong, but look at this, it doesn't say end of file, and it looks like we have a shell, which we do. So now we want to go and test this out on the remote server. So if we go and update our libc library to the remote server version and try and run this again, but this time we're going to say remote. I'm going to copy and paste this server and port number. And we get no such file or directory. So I've obviously named this incorrectly. Let's move libc to this. Let's try that again. And it runs through, but this time we get this end of file. And although it looks like it has leaked the correct addresses, we don't actually have a shell. So this is due to a stack alignment issue in this case, which sometimes I run into problems where I have to change the send line and receive lines between the remote and the local versions, which I thought was the case here, but apparently it was a stack alignment issue. So we can go and insert another return instruction in here. Let me go and let's go back to Ropper. Okay, let's do Ropper -- file, the library. Let's just print all of the gadgets, and you see here we have this return at the bottom, so I'm going to take a copy of that. I'm going to add this as a gadget as well. And then we'll just add this here as well to make sure everything's aligned. That didn't work because I did that locally, and my local version is not using the same libc. Let's try it remotely. And it runs through, it says we're wrong, but this time it doesn't say end of file, and if we try to list, you can see we've got all the files here, and we can cat out the flag.txt. So that's the challenge solved. There's the remote and the local script. We didn't really have to change too much at all. In fact, let me see if this also works locally with that change. yeah, still works locally. So the stack alignment issue needed to be done for the server, but it doesn't break anything on the local side of things anyway. What I'm going to do as well is just copy over another script where I made some changes to this just to show another way that we can do things. So a more automated way of solving this would have been to use ROP objects. So I'm just copying over this other script I put together, and let's compare it. So we create this ROP object here with the elf with the library binary, and this will basically make it very easy to call functions and find ROP gadgets and things like that. So you can see in this case we found the pop RDI gadget using this ROP.find gadgets, but we don't actually need it. Let me just remove that altogether. What I'm going to do actually here is do pprint ROP.gadgets, so we'll print these out at the beginning just to show what that looks like, and then rather than that code that we had previously, which was leaking the elf.got.puts, we can just call ROP.puts, and then that's the address we want to leak, and then we're going back to the main method. And just to show as well, let's do print ROP.dump, and that'll show, we'll basically be able to see how it's putting this payload together. So there's actually been times where I've struggled putting together payloads manually, and I've used this and then studied the output to work out how I could have initially solved it manually. So we'll print these out, and then all we're going to do is we're going to send off that payload. It's going to do the same thing. We're just calling ROP.chain, which is going to convert this into raw bytes. It's building the ROP chain, and that's going to leak our address. We don't need to change any of this stuff here. And then once we've leaked the libc address, we're going to update our ROP object, so it's no longer going to be the pointing to the library binary, it's now going to be pointing to libc. And then we can just call ROP.system, and it'll call the system function, and this is the parameter we want to pass. And again, just build the ROP chain and send it off. So you can see how simple that is. I'm going to call prettyprint ROP.dump again, just so we can have a look at it. And if we run the exploit, you can see first of all we have a shell, which is awesome, but if we go up and have a look at this, we can actually look at what we dumped out there. So you can see that it's built up a ROP chain using the, let me minimize this so you can see it a little better, although can't really see it very well with all this stuff in the background. Let me remove all these core files. So yeah, you can see it's put this together, so it's found the pop RDI gadget for us. We didn't need to define it at all. It has put the bin sh string into the RDI, and then it's calling system. We can go up a little bit more and see that it printed out all the gadgets here, so we just asked it to print out the gadgets at the beginning. And then this is a ROP chain it put together to leak the got puts address. So you can see here it's put got puts into the RDI, it's called puts, and then it's called main, and these are all the addresses that if we wanted to put this together manually. So I hope that explained that well. Anybody who knows how to solve these challenges is probably bored or stopped watching long ago, but if you haven't done a return to libc, or you're trying to learn how to do some tricks in Pwn tools, hopefully this has helped. The next challenge we're going to take a look at is called YABO, or yet another buffer overflow, and the description says some certifications feature a basic Windows buffer overflow. Is the Linux version really that different? So the description is kind of hinting that this is going to be similar to the OSCP buffer overflow, where you have to do a Windows buffer overflow on the exam and also in some of the exercises and preparation. So I've already got the server launched, I've got the file downloaded, let's go and take a look at it. So we'll check the file type first of all. YABO, it's a 32-bit LSB executable this time, so not 64-bit like we were dealing with previously. And if we check the security protections, check sec file YABO, we'll see that there's literally no protections enabled at all. So there's no relro, there's no canaries, NX is disabled, so if we can get some shell code onto the stack, we should be able to get it to execute. There's no pi, so the function addresses and all the data is going to be in the same place every time the binary loads. So let's try and run the program as well, see what happens. You can see here we get running server, so we could try and run that with ltrace and see if it's letting us know what port number it's looking for, but I can't see it there. Maybe we need to convert some of the hex values, but let's just go over to Geardra and take a look at the disassembly. So if we take a look at our functions here, we've got a main function which looks like it's doing quite a lot, but let's try and focus on what we're looking for here. We can see that it's going to do this bind with a socket address and the local 30, which is set to 9999. So let's go and try and connect to that. Let's run the binary again, YABO, and let's try and connect localhost 9999. And you'll see here it says what would you want to say? What would you like to say? And we can see here it's received a connection from, and then we have the IP. So we could go and try and just like put a lot of characters in here and see what we get. Let me put in quite a lot. We run that, okay, it's taken our input. We go back over here, don't see anything of interest. We might want to run this in GDB just so we can see more of what's going on in the background. But let's go back to Girdra and see what's going on. So we don't really need to worry too much about this code here. This is just dealing with creating sockets for different connections. What we're interested in here is this vuln function. So we can see it's going to call vuln. So immediately we can see a buffer here of 1024 bytes, this local 414 variable. We can also see that we've got a local 10 which is calling malloc. It's going to grab F00, which is 3840 bytes in chars, and it's then going to ask us what would we like to say. It's going to take an input off us, and it's reading in 0xEFF bytes, which is 3839, into this local 10 variable. If there's any problems, we're going to get this receive error, and it's going to free that memory. Otherwise, it's going to try and do the string copy, and it's going to be copying whatever's in local 10 into local 414. And we know local 414 is 1024 bytes, and we know that local 10 was, well, it's reading in 3839, was it? Where is it? 3839. So we can see that we've got a buffer overflow there. What we want to do is go and test this out then in GDB and try and find out exactly where the offset is so that we can overwrite the return address. So let's jump over to GDB and try that out. So I'm going to close down this server. I'm going to run GDB pwn debug YABO, and let's run that there. In fact, let me generate a cyclic pattern of, we've got quite a lot of, let me do 5,000 bytes. It's not going to be needed, but let's continue the execution. Let's connect this with our netcat, and let's paste in that cyclic pattern. And you can see it's frozen here. It didn't say, or it didn't exit like it did previously. If we go over to our GDB, we can see that it has indeed hit this invalid address. So you can see the value that's in the EIP is LAAK. So we could just go and look through this big cyclic string and see where is that LAAK, and wherever that is where our offset will be. But we can just do this in GDB as well. So we'll do cyclic-L, look up the offset, and we'll find that the offset is 1044 bytes. So we need to write 1044 bytes before we'll overwrite this instruction pointer. And we want to overwrite the instruction pointer. Ideally what we want to try and find here is maybe a jump ESP instruction, which will make it jump to our ESP, and you can see that ESP has this MAAK in it. So let's just out of interest, let's do cyclic-L, although it's completely predictable. So this is directly after our instruction pointer. So we overwrite the return address, and then right after that we have our shellcode. But although it's right after that, logically we still need to get the address of the ESP. So we still need to find that jump ESP instruction. So let's find that first of all. Actually, let's jump over to ROPR. You can just run ROPR -- file YABO to get all the ROP gadgets here. If you want to search something, you can do search, and we're going to look for jump ESP. We'll find that there is one jump ESP instruction, and this is what we're going to need to go and put into our script as well, along with some shellcode. So let's go and start to build up a script. For this, I actually use some of my OSCP notes based on the description, which has been a few years, but at the time of doing my OSCP I hadn't really used pwn tools at all, so I was writing exploits just in Python and fuzzing in Python and doing everything quite manually. So let's first of all set up a generic kind of Python script to do this exploit. use MSF Venom to generate some shellcode, and then afterwards we'll recreate it in Pwn Tools and see if we can get the same result. So I'm going to create this codium exploit.py. I'm just going to paste in a little bit of template code here. So we're just creating a socket. We're going to connect to our local host on 9999, and we're going to receive. So initially it asks us what we want to say, so we're going to receive that, and then we're going to put a payload here. Insert payload, and we're going to send off that payload here, buffer, this buff variable, and then we're going to receive hopefully a shell or a flag or whatever we're going to set this up to do. So let's start putting that together. So we know that we need a buff is equal to, first of all we'll do a times 1044, that was the offset to our instruction pointer. If we go back here, 1044, and then we know that we need this jump ESP instruction, so we can say buff is plus equal, and then we need to put in our jump ESP, which is right here. If we're inputting this in Python, we'll want to change the endianness of this. We need to write it kind of the other way around. So let's do, so we'll do \x 08, \x 04, \x 92, \x e2. So we're just reversing the order of the bytes, and that should be fine. Now all we want to do is add in some shellcode. We might want to put in some no operation instructions as well, just in case. Probably be fine, but just in case there's we need any slack space, we can say \x 90 times 10. And really you're better off doing this with here as well rather than sending A's, but it doesn't really matter too much. In this case it'll still work for us. And now all we need is some shellcode. So I used MSF Venom to do this. Let's go and generate a payload in there. You can do MSF Venom-L payloads to list all the payloads, and then if we want to grep out the operating system we're dealing with, we can grep out Linux. And it takes a little while to come back with the results, but this is basically what you'll see is used in Metasploit Meterpreter as well. So we could try and get a reverse shell, and this is what I initially did here. Let's try it out just to see what happens. We'll do MSF Venom-P for payload, and we're doing reverse TCP, and then we just input the parameters just like we would in Metasploit. So we'll set the L host to our local address, in this case 127.0.0.1, and you might notice what the problem is going to be here in me saying that. Let's do L port 4444. -B, so you can specify bad characters. In this case we didn't look for bad characters, but I just kind of tested it out first to see if we could get a shell, which it did work for me. So we'll just say that a null byte is a bad character anyway, which it typically is, and then we can specify what format we want the shellcode to be in. So because we're writing a Python script, we want this to come out in Python format so that we can just copy and paste it straight into our payload. You can see we've got a payload here. You can see the encoder it used as well, so we can take a copy of that and just go and append this to our exploit. So we might want to take a copy of the payload that we used and just go and insert it into the comments, so that if anybody else finds this exploit and they want to recreate it, they know what this shellcode is referring to. And let's try and save that. Let's try and set up a shell here on this port 444, so we're waiting for a connection back to us. We need to send off this payload, so we're going to do Python, make sure this is Python 2, and exploit.py, and we need to make sure this is running as well. Let me restart the server because I think that might cause some problems. Now you'll see what will happen here as well. If I try and just run that, I'm going to get addresses already in use. Let me do sudo kill all YABO, try the same again. Let's run it, and let's run our Python script. See, it says what would you like to say, but it's not actually done anything. You can see we've got some things going on here. Let's jump over to our shell. You can see here it says we got a connection. We can do ls, we can do who am I, and you can see that we're now connected with this reverse shell. So the problem is here, of course, we're connecting to our local host, and if we run this on the server, we're not connected with a VPN or anything, so I was kind of sure that wasn't going to be the solution, and indeed we can't get a reverse connection. So there are some other kind of shells that we could try to generate here, some of the shell code. Let me just run through quickly some of the examples that I did. So here's one where I tried to basically use request bin, so set up this little web server and then test this remotely to see if it would actually curl the server. It didn't work remotely, but it does work locally. It will curl this address, so we can go and actually have a look at the request that's sent to it. But it didn't get me any closer to getting things working remotely either. I also tried doing a shell bind, so something like this, and hoping that we'd just be able to set up a new bind port on the server and then connect with netcat to that port. But again, that didn't work for me. So something else that I looked at, let's go back to our payloads, list of payloads, grep Linux. Probably quicker for me to scroll up, but so if we go and run through some of these, yeah, we have this exec, which looks good. We also have a read file somewhere. Oh, it is right in front of me. Yeah, it's right here. So we can see here, and the description says read up to 4096 bytes from a local file system and write it back to a specified file descriptor. So if we were to try and run that, and let's just say read file, and then I think does it ask just for the file? I think it asks for the path. Let's do path equals flag.txt. Let's just test this out locally. I'm going to echo flag fake flag to flag.txt, and let's take a copy of this shellcode, put it into our exploit, and we'll try that again. And you'll see here we get this flag, fake flag. So we can do this remotely. We can just go ahead and update our script so that we have the remote server address and port number in here. But it's pretty obvious what the problem's going to be. This is showing on the server, so we can print the flag, but it's only going to show on the server. And this is a problem I ran into for a good while, which I was trying to resolve. Let me actually just go through a little bit of some of the things that I did try. So one of the things that I was thinking was this send function that we have here. This is being used to send us the message, what would you like to say? So I was thinking if we could recreate this with the same parameters, we could just maybe read the flag and then send that back to the socket. And to try and work that out, I was basically set up a breakpoint here. So let's set up a breakpoint at send on that server. Let's do break start 0x, and let's try to, let me minimize this so you can see it a little better. Let's try to run this again, and we don't get a, let's try and connect to it. We're not getting the breakpoint there. We might need to set up a new connection. Let me do that again. We'll set up the breakpoint again. Let's run it. Let's try to connect. And yeah, it's hit this breakpoint. So we can actually see here exactly what's being sent. So the file descriptor is set to 0x4. And then we have our buffer, which is the message, and then we have the length, and then the flag. So I tried to basically recreate this in Pwn tools and in the Python script so that we're calling this and try to send it with this for, which didn't work, but it did get me closer to what the correct solution is. So let me first delete these breakpoints, and let's do continue, and let's close that down. Let's go back to our MSF Venom command, and we're going to use the same command, but I'm going to change it very slightly. I'm going to include in here fd equals 4. So we saw there that the file descriptor is 4 for that, which is basically just going to determine where it writes the output to. So if we try this again with the correct file descriptor and take a copy of our payload, paste this in here, let's run it again. This time it returns to us this fake flag, which is looking good. So let's take a copy of this server address and port number. Let's go and put this into our script. Let's try and run it again, and this time we get back this flag from the server. So everything's working properly. After I got this working, I also created a PwnTools script to do something similar. So this is just the usual template, and we have our exploit here where we've set our offset at 1044. We've got our jump ESP instruction, the location of it, and we're just creating a payload here. We're going to write 1044, no operation instructions. We're going to do our jump ESP, and then we're going to use shellcraft to call cat flag.txt and pass in this file descriptor. So shellcraft, let me actually just go and open up shellcraft docs. Shellcraft will basically try to resolve things on the operating system. So you see here we have i36 and AMD64, Linux. We also can do Windows stuff on here as well, although I'm not seeing it here, but I'm pretty sure we can do Windows stuff. Where basically, as long as we have the ELF specified up here, we've got this context set. It knows whether to use 64-bit or 32-bit. It knows what operating system we're dealing with. So we don't even need to specify shellcraft.linux.x86. We can just do shellcraft.cat, and then it'll work out everything else for us. So that's going to do that. It's going to write the payload to a file as well, which means we can just then resend it. So let's just test this out and see how this works as well. We'll do this against the. Let's do this against the. Well, we can do it. We'll do it locally. We'll do it against the remote server as well. So because we have this set up locally, we can do Python exploit. Let me do. Well, we still need to do remote because we're testing it against a remote server, even if the remote server is a local server. So we can do localhost 9999. We run that, and we get back this fake flag. You can see there's a lot going on here, but it's just because I have this debug log level set, so we could reduce that if we didn't want all this output. But this is quite nice because it shows you how it's put together, this shell code. So whenever we call shellcraft.cat flag.txt and that file descriptor, this is the shell code that it's generating in order to achieve that. So you can see it's calling send file. It's set the file descriptor for us at 4, and it's retrieving the flag. And again, if we want to test this again remotely, we can just go and grab the server and port number from here, paste this in, and we get the remote server connection and the flag. Because we wrote our payload to a file as well, we've got this payload right here, which means if we were to just run, let's see if we can just run netcat. I'm not sure if we can paste this in this way. It's been a while since I did this. Yeah, we can. Okay. Alright, so we can literally just send off this payload, and that'll retrieve us the flag. The next challenge is called Phonetic. It's a malware challenge, and the description says it's easy to find the flag, just sound it out. So we've got this file to download. I've already downloaded a copy of it, and we can see right there it's a PHP file, which we could also verify with the file command, and we want to move it to phonetic.php. And let's open it up in Codium and take a look at it. So straight away we can see we've got quite a lot of obfuscation here. We've got some kind of loop going on here, which is looping through to the string length. But it's going to be pretty hard to decipher this just by reading through it. We've also got a big block of what looks like some encoded text. And if we scroll right down to the bottom, we have some more code here. So we've got another for loop and 2 for loops, and then we've got this code as well as some comments which we can't read either. So we might want to go and take these to see if we can throw them in some kind of decoder, maybe even just put them into CyberChef and the magic function to see if it decodes anything. You can also find some PHP deobfuscators online, but I didn't try any myself. The first thing I did here was try to run the PHP script. So we can run php-f and then phonetic, and you can see it actually prints out this HTML page. So let's send that to new.html. And let's open that up with Firefox. Open that up, and we have the source there, but yeah, it's just a 404 not found, so it should be a username and a password box by the looks of it. but let's move on anyway. We can make some changes to the script, so we might want to go through and add in some commands here to print out some of these different variables and see if we can work out what they're doing. So let's start with this first loop. We've got this variable here, which you can see it's concatenating some different elements here. So let's just say we want to echo out that variable. Too many dollar signs. And then we can put a semicolon there. Let's run this again and see here that we've got a base64 decode. So this first function, this is the string that's creating base64 decode. So what I would personally do here is Control and F, and then we'll replace all instances of that with base64 decode. And we can basically keep going through in this fashion, see if we can work out what's going on. So again, let me just copy this and we'll echo this out. Run it again and see that this time we have a string reverse there as well. So we'll just search for this string, change that to str reverse, replace all of those, and we can keep going through in this fashion. So what else do we have here? We've got a k is equal to string reverse, so let's print out k. And where is that printing out? Oh, create function, okay. So this one is create function, so we want to make sure we go for whole words here. We want to replace, because that K is going to come up in some different places, so we want to replace this using the dollar sign as well. Replace all of those, let's create function, and we can start taking some of these out as well, just so that we're not seeing those all on the output. And we have this C as well, let's print that out. And this is lambda 1, take a copy of that. Replace the C with lambda 1. And it's starting to come together, so we can see this base64 decode here. I'm interested to see what the result is of this. So if we take this value, let me try and take this whole thing here. Well, we'll take the base64 decode bit. I'm going to say new is equal to that. Okay, it looks alright, and then we want to echo that out. And let me clear this so we can see what's going on. We run this again, and this time we get a lot of code. So it's actually decoded that whole script for us, which is awesome. Let's send the output of this to, was it printing something else out? Let's not call this lambda function. I'm going to send this to stage1.php. Let's open that stage 1 and take a look at it. So there's a lot of code to go through here. The first thing we notice here is we have an auth pass. So if we actually take that and even just go and search it in Google, we'll quickly find that this is an MD5 of this password here, I guess, or this string, which I thought might come in handy, but it actually didn't seem to. We could also go and just search for other parts of the script. If we search for other parts of the script online, we'll find that it's a common PHP web shell. So you can actually download that PHP web shell and then do a diff. But due to a few, I mean, it's not particularly easy to see all the differences, because a lot of things show up differently, maybe just due to minor syntax issues, spacing and things like that. But yeah, a lot of functions in here. If we scroll down towards the bottom, we have some values here which we can see the double equals look like they're base64 encoded, so let's take those to CyberChef. And we can base64 decode this, so we can actually see the set to bind port P and then back connect P as well. So it looks like this is going to be getting a reverse shell, getting a shell. So let's base64 decode, and this, yeah, so we can see here it's calling bin sh, it's echoing the string, then bash. Let's have a look at the other one as well. just add this so we can see both of them. So we have this one down here as well. And I moved on from this a bit too quickly and carried on looking through this code and didn't find the flag. So it was actually one of my teammates that found the flag here. It's in this code. I just overlooked the section here that says begin 644 and then URL encode.uu. Let's go and search for that. Or yeah, UU encoding is a form of binary to text encoding originated in Unix programs, and we can decode this in Python. We also have a decode.fr link, so hopefully we'll just be able to do this online if we take this string and paste it in here and then decrypt, and we get the flag. The next challenge is called Confidentiality. It's a web challenge, and the description says, my school was trying to teach people about the CIA triad, so they made all these dumb example applications as if they know anything about information security. Can you prove these aren't so secure? So we've got this web server which will launch in a new window, and we've got a text box here which is asking us to input. It's given us an example here for etc host. So with a service like this, you might see the simple access control settings on any file you like. So let's just try and go for the default behavior here, etc hosts, and we can see that it's actually telling us the permissions here. So it looks like it's running an ls on the etc hosts. Let's try and inject a command as well. So we could say etc hosts, and then let's try and put in a semicolon to end that command. And let's try and enter another command like ls, or we could try a couple of commands ls. We could do who am I as well, and assess confidentiality. And you'll see here that we've got our who am I was user, we've got our ls has produced our flag.txt, main.py. So presumably then we can just inject a semicolon here and say cat main.py, and we can print out the whole Python script that's running here. Obviously that's not what we're looking for, so let's instead do cat flag.txt, and there we have our flag. The next challenge is called Integrity. It's a web challenge, and the description is the same as the confidentiality challenge where we used command injection. So they've basically tried to fix that by the looks of it, and we need to prove that it's still vulnerable. So we've got this site to connect to. Let's go and take a look at it. And you can see it looks very similar. The last one was telling us what permissions we had, so it was running like ls, and this one is running SHA-256. So let's just try the default, the intended behavior first of all. And if we do that, it'll give us the hash for etc hosts. So let's try then and insert a semicolon like we did last time. But this time you can see it's been rejected. We're not allowed to insert that. We're not allowed to insert pipes. We're not allowed to insert and. Probably not allowed to insert much. Yeah. So whatever we try to insert here, it's not going to work. I was kind of thinking that maybe I was hoping we'd be able to use a dash and maybe append to the SHA-256 command. I did a challenge a while ago where we were able to get the SHA-256 of each character in the flag file and then crack each of those hashes. So I thought it might have been similar. It's not, but let's have a look then at how we can solve this. So I'm going to go to Burp Suite. Let's take one of these requests and send it to the repeater. And we can go to look for some kind of cheat sheet here. So let's look for command injection filter bypass cheat sheet. There'll probably be plenty available. I normally go to Hacktricks just to find the layouts quite nice, and they've got some good examples to run through. And you can see right here we've got some examples, and if we were to run through some of these, we could actually just like set up a word list in Burp Suite or something to run through and try these. But if we start running through and trying these, and we get down to this one here where we have the new line character, it is provided in the URL encoded format. Take a copy of that one and submit it as the file. We don't even need to worry about the spaces there, and you'll see it's come back with the user, and again we can modify this. We'll change that to ls, and it comes back with flag.txt, main.py requirements, etc. So now we can just go ahead and say, alright, we want to cat the flag.txt, and we get our flag. The next challenge we're going to take a look at is called Availability. It's a web challenge, and the description is the same as the confidentiality and integrity challenges. This is the CIA triad, so we're onto the third stage of it, availability, and the last two stages were command injection, so it's likely we'll be dealing with something similar. The update we have here for this specific challenge says, they said they fixed the bug from the last app, but they also said they knew they went overboard with filtered characters, so they loosened things up a bit. Can you hack it? And we've got this address to connect to. Let's go and take a look at it. So we've got a ping service here, and it's suggesting we try to ping the local host 127.0.0.1, and we get back this message say it was successful, it was able to ping that address. Let's try and put in an invalid address to see. Yep, we get failure in this case. So in the previous example we'd used a new line to concatenate commands. Let's actually go and open this up in the repeater, and let's try, just first of all, we'll just try and append a semicolon, an ls, and if we do that we'll get this message to say that character is not allowed. So let's try it again with the percentage, where's it gone? Percentage 0a, which we used previously, just the URL encoded new line character. And if we do that, we get success. Looked like pinging the host worked. So we're able to inject that command, and it looked like it executed successfully. The problem is it's not bringing any output to us. The only thing it's going to bring back is to say whether the command ran successfully or whether it failed. So my teammate who originally solved this found that we can use command injection to use these error messages, the success or failure, to determine what the flag is. So instead of doing ls here, what we could do is say we want to grep out flag from flag.txt, and if we send that off, you'll see we got success, looked like pinging the host, and then grep flag.txt works. So we're grepping for the word flag in flag.txt. Now if we change this to flag in capital letters, we're going to get back a message to say that it failed. So this message, success or failure, will allow us to determine what's in the flag. So if we were to now say flag and then provide, well, we can't actually provide, let me actually just show this. If we try to provide this with the curly brace, we're going to get a message to say that's not allowed. What we can do is put a dot here, and then we could go through and try and work out what the first character of the flag is. So we get a failure on A. Let's try a couple of characters. We try B. We get a failure on B. Let's try it with C. And we get a success with C. So we know that the first character of the flag is going to be a C. And now we can basically go through the same process. Let's do A. We get a failure. Let's do B. And we can basically work our way through and extract each character of the flag this way. So it's kind of similar to the blind SQL injection challenges that you might have done in the past. What I'm going to do to solve this is grab a script which I used in the Hack the Box Cyber Apocalypse. There was a blind SQL challenge, blind SQLI challenge there. You can see the script that I created at the time, where we basically start off with what we know the flag is going to begin with. We loop through the ASCII characters, the lowercase strings, and then because their flag also contained a mix of different characters, we have to deal with a bit more, and we basically just do the same sort of thing. We're sending off the password and we're working out what each character is. If it comes back and says successful, we know that that character is correct, and then we can restart and move on to the next character. So I basically took a copy of the script and then modified it slightly. So let me just copy over the script. Okay, so this is a script that we have here, and we've got the address in at the top. We're starting off with our flag dot because we know that it's going to begin with flag and the curly brace, but we can't submit the curly brace because of the encoding. And we're basically, just as in this example here, we're just looping through, and we're going to restart each time we find a correct character. We only need to deal with ASCII, lowercase, and digits in this case because it's going to be a 32 hexadecimal character flag, as we've seen in the previous ones. And we're going to loop through each one of these characters. We're going to try and send this off with this grep and see if, so we're going to start off, for example, with flag.a, then flag.b. We're going to go through till we find that flag.c, and then we restart because we find success in the response.txt. We'll restart, and then we'll go for the next character. We'll keep going through until we have flag, curly brace, and then 32 hex characters, and then we know that we've got a full flag. we can just replace the dots with the curly braces and print out the flag. So let's test this out. If we run Python exploit, you can see here it quickly got flag C, and it's going to take a little while to run through and get the whole thing. Let's just wait and see if it gets the second character before. Yeah, so it's found the first two characters, so we basically need to leave this until it's got all 32. I'm going to speed through the process here a little bit. Okay, so it took about 5 minutes to complete, and we get our flag, and we can just go ahead and submit that. The next challenge is called Swaggy. It's a web challenge, and the description says this API documentation has all the swag. So we've got a server launched already. Let's go and take a look at it, and it takes us through to this Swagger UI. So whenever I see challenges like this that look quite realistic in terms of the application, where it looks like there could be quite a lot of stuff going on, I'm immediately kind of daunted by the potential solution. But actually in this case this was quite an easy challenge to solve. We have a production server here. It says currently unavailable, and we have a staging server for testing. So this currently unavailable has a basic auth, which I just tried to put admin into. I don't know whether that's even required. Let me just try and do, I don't know, root and tour to see whether it's any different. Authorize. Okay, so it's given us this basic auth. I'm just trying a different username and password because I'm not sure whether whenever I solve this the admin had any impact at all. And that's authorized, so we have this now. We can try this out, execute, and you can see here what it's calling. So it's going to retrieve a JSON object containing the flag, and it's calling flag md5 sum rand. Okay, let's let me try to change this to the staging server. Hit cancel. I'm going to try it out, execute, and we get invalid credentials. Okay, so let me try that again. Log out. I guess the admin was right. So we'll do admin authorize, and let me try and execute that again. This time we get back this flag, and I think this is actually the flag. Although what I did here was to let's see if this is the flag. So what I did here was to go to burp suite, and we have this command that we sent off. Let's try and send that to the, where's that, staging? That's a server for testing. Let me change that to API. So the only difference is this one is API instead of staging API. So I'm going to send this to the repeater, and in the repeater let's take out the staging bit and send, and we get the flag there. So it looks like it's the same flag. Yeah, it's the same flag. Alright, I think it would have been cooler if there was an extra level to this where we also had to set this to the actual API. But there we go, we've got a flag. Easy enough challenge. The next challenge we're going to take a look at is called Titanic. It's a web challenge, and the description says TTEC is a rising cybersecurity organization which creates tools and provides cybersecurity solutions to its clients, but are they themselves secure enough? So we've got this web address to connect to. Let's open it up, and we can go and start having a look through the site. I didn't actually solve this challenge. It was solved by a teammate, and I went down a few rabbit holes when I was trying to solve it, but it's surprisingly simple. So let's run through the solution. So we've got a couple of links here. The links basically just anchor us to different parts of the same page, but we could have a read through some of the text to see if it's got any hints for us as to what the challenge is going to involve. We've also got an admin page here, admin.php, which we can go and try to log in. So we might try some default credentials, admin password, things like that. We might try and put some apostrophes in here and some quotes to see if we get any errors. But no matter what we enter here, we're not actually getting anything of interest back. We can go and have a look at the request in Burp Suite to see if there's anything interesting there. Don't see any cookies or anything like that. So at this point we need to go and have another look around. Let's go back to the main page, and if we're actually on the main page and have a look at the source, what I noticed when I was just scrolling through here is we have this URL capture.php. You can see here latest tool URL capturer, which if we scroll through the page, you don't actually see any mention of here. I guess it's kind of hidden with some of the CSS or something, because if we do Control and F, we will find here, or maybe was it at the top of the page, I just missed it, maybe. So we can click to check out the URL capturer, and it allows us to put in a URL here, and it's basically saying it's going to grab a screenshot of it. So let's just try and put in the URL that we're on. Some URLs you provide it will take a long time. You can see here, in case of error or the image being empty or doesn't change, you have blacklisted characters in your URL, and you have this filtered URL here. So I was thinking maybe there was some command injection or something, and trying to inject some different values in here to see what we got back with the filtered, but it takes so long whenever there's an incorrect value in there. It can take so long to load the page that it becomes quite hard to test. I also tried with connecting to a remote web server, and in that you can see that the header is set to cktivityCon, which we have here in Linux, a tool which will basically grab a screenshot, the URL you can see here. So I was looking through some of the options in here to see if maybe we could, if there was some kind of exploit available for this, and if you have a look online, there are actually some exploits for this. So in terms of taking a screenshot of local files and sending them to the temp directory so that we can then access them. So I was kind of playing around with that for a while, but didn't get anywhere. I was also thinking maybe if we took screenshots of, for example, the admin page, maybe because this is on the server side, maybe the server was logged in as admin, and taking a screenshot would take a screenshot of the admin page, which would have a flag in it or a password or something like that. But yeah, it wasn't really getting anywhere, and at this point my teammate found something which I used to check, used to be the first thing I would ever check on a web challenge, and haven't checked it in so long in CTFs because it just never seems to come up anymore. But if we have a look here, there is a robots.txt file which has this server status, and we can go back here and try and input that. If we try and input it directly, I think it's just going to kind of struggle to load, take a long time taking the screenshot. We could try with the full URL as well. Let's try and check that. But I think it's just going to take a long time to come back. So what we need to try and do here is instead use the local host or 127.0.0.1 address. Let's try localhost. Okay, that did still take about a minute or so to come back, but you can see we have the URL up here set to server status. Oh, so that didn't actually have the local host there. Let's see if it brought back. Okay, no, it's a blank page. Alright, so let's go back and this time do it with localhost. I think it should come back quite quickly because there's no errors. It does, so we'll try and open up this captured URL. And this basically gives us a screenshot which we can start to have a look through some of the information here, and we'll see that there is a GET request to admin.php with the username root and then this password here. So we basically just need to type out this password or this URL, and then we can go and try and visit it. So I've got a copy of that password. Let's go to the admin page, and the password, the username is root, and the password is the one that I've just copied, and there we have our flag. The next challenge I'm going to take a look at is called OPA Secrets. It's a web challenge, and the description says, OPA, check out a new secret management system. So we've got this website to connect to, and if we open that up, we'll see this OPA Secrets, please sign in. As usual, try some default credentials, admin. We get invalid. We could try and put in some quotes here to see if we get any errors back, and we don't. So let's have a look at this sign up and try and create a new account. Let's see if we can create an admin account, or whether it tells us the users. Okay, let's just create the account. So we'll log in as admin, and we can now see that we have access to this Your Secrets page where we can create a new secret. We've got a security page which says, this service has been implemented using the latest access management technology to ensure your secrets will never be accessed by unauthorized parties. All of our code is open source, so it can be reviewed by security experts to ensure there are no vulnerabilities. Check us out on GitHub. So we can go and take a look at the source code here, but let's go back to our secrets page here as well. Just out of interest, if we try and put in here test and test, we can add a secret, and you can see now that we can view the permissions of the secret. We can go and have a look at some other users here which we can make some changes to. So let's go and say, let's add this Pinky Koala. Let's say that they can read and write the secret. It allows us to do that. We can create another one. We can view the secret here as well. And this just means that we can go through now and have a look at some of these requests in Burp Suite. We can see what's being sent, what's being received. You can see we have the JSON object here with the secret ID, user ID, reader, writer. So these are some parameters that we'll be able to go and play around with based on what we've just filled in. But let's go and take a look at the source code and see if we can identify any vulnerabilities. So we have some code here. Let's go and take a look at the application, app.py, and we can start to have a look through this. You can see first of all there's a test secret here. We have some users. We've got the admin user, which we just saw whenever we were trying to set permissions as well. We have another user, JellyTalk, who is a user, and Pinky Koala as well. And then we have some test secrets here as well. So we've got test secret 2, and we also have this flag, which is going to read an environment variable called flag, which has a test flag in it. So we have potentially here already an ID of a secret that we want to retrieve. We also have some user passwords as well. Why don't we go and try some of these out? Let's go and log out as this admin account and try and log in as an actual admin. See whether this password has been changed. We try to sign in, we get invalid credentials. So that one has been changed. We could try some of these as well, although unless they own the secret, it's not really going to be too much use. And if we go down and have a look here, we can actually see that the permissions are being set here. So you can see that we have the add secret here, the users are being created here, we have the secrets being created, and then it's assigning the first secret to the first user, which is admin, and that's the secret that we're interested in. So we know that this secret is owned by JellyTalk, and the next one is owned by Pinky Koala, but we want this one. So we were able to log in here anyway, but now we want to try and see if we can actually access a secret that we don't own. So that was a test secret. Let's go to the Burp Suite and send this to the repeater. Go through to the repeater and let's take a copy of the flag ID that we want to retrieve. Just keep that open there. We send that off and we actually get our flag straight back, which is interesting. Whenever I solved this initially, I went through quite a lot more steps than that. Let's go and base64 decode that. In fact, why am I going there? We can do this in Burp Suite very easily. So you can see because I had that copied, it automatically decoded that. But yeah, apparently not. So I guess we didn't even need to update that. I thought we needed to go and update this to be the admin cookie. And then I also tried to modify some of these requests to add permissions and change permissions, and that's kind of why I thought that we needed to do some extra steps there. For example, if we try to edit the flag, let me see here, this is the add permissions, let me send that to the repeater. If we try and edit the flag, the secret, change this to flag, and do this as our current user, you'll see that we get only the owner of a secret can modify the permissions. So what if we try and change this user ID to admin? So here's the admin's user ID. Oh, it's already actually set to that because that's the user that owns it. Alright, so why don't we try and change it to the user that we're logged in as? See if that allows us to modify it. Nope, so it has to be the same owner and it has to be the secret. So what we do need to do then is update this cookie. So if we were to go and decode this and then put in the admin ID here, we can encode that, grab a copy of that, and then go back to our repeater. And now if we, let me maximize this, now if we update this session and hit send, this time we get 302 found, and we can go follow the redirection. Basically it takes us back to log in, but it should have added the new user to the user that we set to that for admin permissions. I think I actually added the permissions of the admin there though, so that didn't really make sense. But anyway, I guess that wasn't necessary. All we actually needed to do was just request the admin flag, and that seemed to work okay. The next challenge is called To Do. It's a mobile challenge, and the description says, I made my own app to remind me of the things I need to do. And we have this todo.apk file to download, so I've downloaded that already. I'm going to open this up with JADX GUI, which will allow us to decompile the code basically. Another option is, which I've dealt with on other Android challenges, would be to use APK tool and then d to do, and this will basically extract all the smally files, which isn't, we want the decompiled code here, which, let me just open up to show what we're looking for. Here we have the to do, you can see to do here, and we're basically getting the Java code back. But if we wanted to modify some of the code in the APK and recompile it, we can use APK tool to extract this, and then we could do codium to do, and we can basically open up all the extracted smally files, and that means we could go in here and modify what we need to. So this was the to do. So let's look at the difference. To do.smally, you can see this is basically the assembly code, whereas this is our decompiled Java code. So if we wanted to make some changes, for example, there might be a condition somewhere. I don't see any conditions there. Let me try and find one. So you might have a condition somewhere which is saying if equals or not equals, and it might just be a case of literally just changing it. So if you had a condition that says if password equals, and it's doing some password comparison, you could say if password not equals, and then basically any password but the correct password would work. And then you could go ahead and recompile this and then go and debug it or run it in Android Studio. But I just thought I'd show that quickly. It's not needed for this challenge anyway. If we have a look at this challenge, we've got our main activity here. We have login activity, which sounds interesting. And you can actually see here in the login activity, it's checking does the string equal test test. If it does, it's going to do start activity. Otherwise, it's going to say wrong password. So we know the password is test test. We could potentially go and just decode this a bit further and try and find out what the flag is. But what I did at this stage would be to open this up in Android Studio. Let's go Android Studio bin, and we'll run studio.sh. So with this open, you can see I've already imported the APK, but you can basically just go to Profile or Debug APK. You can select that. Let me reload this in this project. So you can reload it, and you can have a look at some of the files in here. I think this gives us access to the smally files as well, if you want to have a look at that. Let me double check. Yeah, so we can actually go and have a look at the kind of assembly code here as well, and we can have these run on different Android devices. So I've set up a Pixel 5 running Android 8.1. You can try some different ones. Sometimes on challenges you need a specific version or within a certain range, but with that done, we basically just go and say that now we want to run or we want to debug. I'm just going to run it, and let's try and run it now. Okay, this is an error I ran into last time. Alright, let me try and invalidate caches and restart. I'm not too sure why that's happening, but let's do that, and let's now go and profile debug, select the APK. I'm going to create a new project just in case that's causing any problems. Okay, we've got to do here. It's not letting me select the pixel, but it does seem to be loading the emulator. There we go. Okay. You can see it actually popped up with a flag there from the last time that I ran this. So we're running this fresh. It's got the to do app. It's asking us for a password, and then we enter in our password, which was test test. We submit it, and then we get a message with the flag, and it says use actual encryption, not just base 64. So I guess there was some base 64. You can see here base 64 decode to do. So we could have probably solved this without using an emulator at all. The next challenge is called Shelle, or Shelle. It's a misc challenge, and the description says Professor Shelle created a custom pseudo shell for us to learn Linux. She believes it's safe and no one can read the flag. Can you prove her wrong? So we've got this netcat server to connect to, and the server's running at the moment. My teammate actually solved this while I was working on the challenge, but let me just run through the solution anyway. So we connect to it, and it tells us we can enter help to see what commands are available. You can see that we can run whoami, we can run print working directory, ls, we can have a look at the processors, we can check ID, we can echo, and what was the final thing? And we can cat as well. So we can try and cat, let's try and cat flag.txt for example. There's no flag.txt here. We've got assignment and we've got bin. Let's cat assignment.txt, and this prints this out. It basically tells us that there is a flag in the opt directory and that we need to try to print that out or answer all these questions, which are part of our homework. So we could try some commands, like if we run ls, let's see if we can actually pass in options, which we can. So we can pass in options to some of these functions. If we were to try and just cat out opt flag.txt, then we get this illegal character found for your own safety, and this applies to a few things. So we can't use semicolons, we can't use pipe, we can't use and, we can't use dots. Oh, we can use dots. Maybe it's just a slash I was missing there. Yeah, the characters that we can enter here are quite limited, but let's have a look. If we go back to, let me go to open up a new terminal, and if we have a look here at the manual page for echo, there is a -e flag which will enable the interpretation of \escapes. So if we go back here and say echo -e and then pass in a \x41, which is capital A, and you can see it actually prints out capital A. So let's try and do, let's go and open up CyberChef, and we'll try to grab the hex value so that we can go and list the opt directory. So we'll do 2 hex, and we're going to use \x because that's the format we need it in. Let's put in here opt. Let's grab the, what did I just do there? \opt. Let's grab this hex value and let's echo that out, and we get echo -e, and we'll print out opt. So now we can just try and say, well, if we do ls and then pass in another command, in this case echo, so we're passing in the, we're going to execute echo -e and /opt inside of these brackets. This is going to be executed, and then the result of this is going to be passed to ls, which means if we run that, we'll see that we've got this flag.txt in there. So we know the name of the file. Let's go and update this to flag.txt. Take a copy of those hex values, and let's just do the same thing again. So this time we want to cat, and what we want to cat out is the result of this echo -e with those hex values. We run through that, and then we get our flag. The next challenge is called Jed Sheeran, and it's an OSINT challenge. The description says, oh, we have another fan with a budding music career. Jed Sheeran is seemingly trying to produce new songs based off his #1 favourite artist, but it doesn't all sound so good. Can you find him? And we're told to find the flag somewhere in the World Wide Web, where the World Wide Web, where with the clues provided. So let's just go and search for Jed Sheeran, and we'll very quickly find this SoundCloud account, and we can just go and explore this. So we can quickly see here, was there a comment on one of their posts? I think it was this one, a repost. You can see here we've got 3 comments. So if we click here, we've got a flag very quickly. What I would have done if the flag wasn't here would have probably been to start looking for the images, although these look like some quite common images, but you can go and search for these on like TinEye or Google reverse search. We could also go and have a look and see who they are following or who the followers are to see if there's any kind of linked accounts, etc. But yeah, easy enough OSINT challenge. The next challenge is called Mike Shallot. It's an OSINT challenge, and the description says, Mike Shallot is one shady fella. We're aware of him trying to share some specific intel, but hide it amongst the corners and crevices of the internet. Can you find his secret? So I didn't actually solve this one, this was solved by a teammate, but let me run through the solution. I initially thought this was going to have something to do with the dark web, because John Hammond did a video series quite recently going through looking at darknet marketplaces and dark web search engines and things like that, and I figured it would be related, but I didn't find anything on any of the deepnet search engines which he had covered in his video. So what we can do here is go and have a look for, see if there's any usernames like Mike Shallot. We could also go and try to do some just searching on Google. Let me go to google.co.uk or .com, and we can try to search like sites, for example Pastebin, because it said there that they were sharing some specific intel. Pastebin's quite a popular site to dump data on. So you could say site Pastebin. We could be trying to look for Mike Shallot. We could try that, not find any results there. Let's try it with, I'm missing pastebin.com, that's why. And then we could basically go and look through some of these options. We're not going to find anything that way, but let's try and have a look to see if we can look for a username. So we can go to something like instantusername.com and just go here and search Mike Shallot, and this will check the various websites, social media sites, GitHub, things like that, to see where this username is already taken. So we know it's not GitHub, so they've not leaked anything on there. It's not Twitter because that's available. But if we go through these, we'll find that the Pastebin link is taken. Where's Pastebin? So Pastebin's taken, so let's click here and go to Mike Shallot, and we see here Shallot summons, and we have a message saying, this site is not as safe as we need it to be. Meet me in the dark and I'll share my secret with you. Find me in the shadows, these may act as your light. And we've got an address here which looks like an onion address, and then we have another string here as well. So you could take this over to the Tor browser, you can download like a portable version, or you can try and find a proxy. So there are some sites online which will let you connect to an onion site if you're not too worried about your actual privacy. Let's see, Tor proxy. Tor proxy web, let's try this one, foreverproxy.com, and you can see here it'll allow you to access onion sites directly in the browser without Tor, just paste in the website. So let's try and paste this in as a onion address, .onion, and make sure it's a valid domain first of all, and that loads. We don't get anything here. You can see here it's a paste, looks a bit like Pastebin, quite a simple kind of paste site, but what we missed there was the directory and the file name. So you can see here we've actually got this path that we need to also provide, so let's insert that as well. Go to site, and eventually it'll load up with our flag. It says, you've met me in the shadows and you seem to know your way around the dark. I will share my secret with you. And there's the flag. So I'm going to wrap the video up here as we're over 2 hours at this stage. Big shout out to the Hacktivity crew and all the challenge creators, especially John Hammond, who celebrated his birthday by hosting the CTF, which is pretty awesome. Shout out to the team as well, Duck Society. There's quite a few other challenges here which they solved, which I was going to record walkthroughs for as well to include in here, but I think 2 hours is a long enough video. I need to go through and edit out as many microphone pops as possible and try and get it ready for YouTube. But thanks for watching, hope you've enjoyed it. If you have any questions, comments, leave them down below. Thanks.